of the Kinetic Newton Program seminar series. We always have it on Tuesdays from 2 to 3. And we're very happy that we actually started in person today. So thanks to them for making this happen today. And our first speaker is Gualdani. She will also talk next week. And today she's going to talk about the Landau equation, tutorial part 1.
Thank you very much. When I was asked to prepare this tutorial, they told me explicitly it's targeted to graduate students. So, so perhaps I will speed up a little bit on the details at the beginning. So this tutorial is on the Landau equation, and today I will focus on the homogeneous version, and next week I will talk about the inhomogeneous equation. So the Landau, this equation was derived by Lev Landau in 1936, and his goal was to formulate a new PDE that models the time evolution of colliding particles with Coulomb potentials. So this, the reason why a new PDE was somehow needed in this case is because the Boltzmann equation, which would be a preferred candidate, right, to model colliding particle, is somehow ill-posed for this particular situation. And why the Boltzmann equation is ill-posed for Coulomb potential? Well, we can see this from two sides, the physical somehow and the mathematical. The physical is that the model was conceived by Boltzmann for situations in which the momentum exchange through collision is finite, is well defined and is finite. So the mathematical reason why the Boltzmann equation is imposed is actually a very simple computation. So the Boltzmann collision operator for Coulomb, okay, is ill-posed. And the reason is the following. So if we consider the classical Boltzmann collision operator, which I write in somehow a compact form. So we have the kernel, okay, so it's usually a function of the difference of the pre-collisional velocity and then the element of the sphere, and then we have the classical pre and the post-collisional loss and gain term. And if we look at how this kernel, the kernel B, could look for when we put a Coulomb potential, this kernel would be somehow proportional to a singular term of power 3, but this is not the problem, times a 1 over sinus to the power 4 of theta fourth. So, and then if we want to look at the exchange of momentum across collision, okay, one has to consider the integral on the sphere of this somehow of the kernel times the element v minus v star. And after a couple of integration by parts and transformations, we see that this is actually proportional to something which is, well, the limit, right, when this theta goes to 0 of a term which is okay, so it's v minus v star over the power 3 times, and this is the tricky part, the log of a sinus of theta over 4 or theta over 2, something like that. So obviously this limit is not well defined. Okay, so there is a logarithmic singularity that appears in the kernel, in the Boltzmann kernel, when we consider Coulomb potential. So this problem was actually known by Landau, and therefore he was looking to look. So he was actually studying hot plasma, and in hot plasma, one of the main characteristics is that particles can collide from very large distances in the velocity space. And this collision actually very changes their state. So the exchange of momentum is very small. Okay? And so in plasma, especially in hot plasma, particles arrive at very large but opposite distance. Okay, and this distance means velocity, right, in the velocity space, and are deflected only by a small change in momentum. So this condition, this small change in momentum, is actually crucial in the modeling, because only in this case, so then he formulated that, well, then the evolution of the particle density can be modeled by a Fokker-Planck type of operator. Okay? Really, because the Fokker-Planck operator models phenomena in which really through collision you have a small change in your system. So then he said, okay, the main operator is in the Fokker-Planck form, and S is the flux. Okay? And of course, it's now a nonlinear flux. Okay, it's nonlinear. So then the Landau's effort was to say, basically to find out what S is. And the final formulation of the Landau flux is the following. So it's an integral over all velocities. So we have a singular term, that is the difference between the two velocities, a matrix, the projection matrix, and then we have two terms, and those two terms, they have lost completely this dichotomy characteristic of Boltzmann, the loss and the gain. There are two, but they are not, you should not interpret those as gain and loss. So it's f of in V star, the gradient of f with respect to V, minus f of V, gradient of f with respect to V star, all integrated in dV star. And here I'm abusing the notation in the sense that when I write f of V or f of V star, I actually mean f of V comma t and f of V star comma t. So I'm not writing t, but the time variable is there, of course. So where do all those terms in the flux come from? So this one is quite standard, comes from some formulations when we look at the probability of collisions and the jumping among two particular momentum. But this is very interesting. So this matrix P is the projection matrix, and somehow it's the hardest part in Landau. If you will see that later when we look at some analysis, and it's the projection metric that, so let me write a simpler variable. It projects every vector in the space orthogonal to Y. Okay. The standard projection matrix. And this one, how does it appear? Well, it appears if we assume that if we are at equilibrium, then our flux has to be zero. This is what Landau imposed. So at the local equilibrium, the flux is 0. And then if we go through the computation, we see this projection metric appearing in the flux. And this first, the kernel is a consequence of the Coulomb potential. Okay. I think I would like to clarify is that the exponent then we have here and the exponent then we have here is not the same. It's the same by chance. So, but what I mean is that if I take another exponent in this say here r to the alpha, then here I will not have just alpha. I will have an alpha star computed by following the same derivation. Okay, but just by chance for Coulomb, the two exponents are the same. Okay. So then this is the flux that Landau computed in 3 dimensions. One can do the same thing when d is greater than 3, but today I will just focus on the 3-dimensional case. So the diffusion, so my first remark here is that if you look at this flux, one should see that the diffusion is anisotropic. So it depends on the direction, and that is easy to see because if we now focus on, so if this is the direction of the vector v minus v star, well, it's easy to see then there will be a small cone that is centered around v minus v star, in which, well, if the gradient of, if say the gradient of f belongs to this cone, well, this scalar product is very small, right? Because the p projects the vector on the space orthogonal to v minus v star. So if the gradient of f belongs to the green cone, then the scalar product is very small. On the other hand, if we look at the orthogonal direction and if, say, the gradient of f belongs to that cone, okay, to this one here, right, then here p x somehow, so p gradient f, p acts almost like the identity matrix, right? It's almost like gradient f. Okay, so there is a certain degeneracy somehow in the flux, and it depends on the direction of the gradient. But why did I mention diffusion? Right? Why did I say diffusion? Well, this one can be seen if we rewrite the Landau equation in an equivalent form. So assuming that assumes that f of v and t is smooth, then the Landau collision operator can be rewritten in, I think, at least, okay, and for me, they are the most important ones, 3 equivalent formulations. Okay. So if we start with the original one, so we have this divergence of this vector, so we have the projection matrix v minus v star over v minus v star, okay. And then we have the 2 terms, f of v star gradient f of v minus f of v gradient in v star, in the v star. So assuming then f is smooth, we could break the integral into two terms. And we notice that in every term, there is a term that depends on v, not on v star. So one could bring it outside the integral. So we get the divergence of, well, the first term can be rewritten in compact form as a matrix, capital A of f, times the gradient f. And what is capital A of f? When capital A of f will be what remains here, right? So it's going to be this matrix, this kernel, and the f. So A of f is exactly the integral in R3 of p over the kernel times f dv star. And in the second term, I do the same. This f, the first f of v goes outside. Okay. And then we are left with the integral in R3 of the projection matrix over v minus v star. And then we have the gradient in v star of f of v star dv star. And now to simplify this term, which looks a little bit complicated, I do the same. I do the following. You see that this is a convolution, right? So it's two terms in v minus v star and another term in v star. So I can bring this derivative outside, which becomes then a divergence. Remember, I have a matrix. And then since it's a convolution, I can move it to the other term. And so, we see that the divergence of this matrix here is nothing but, I have done this many times, so I know by heart, but it's not, but believe me, it's negative 2 v minus v star over v minus v star to the power 3, okay, which is something like negative 2, the gradient of 1 over v minus v star, okay. So if I do this, then I can bring the gradient again, and you believe me if I write this compact form minus f of v, the gradient of little a of f, okay, where capital A is defined here, and small a is negative, is 2 the integral of f of v star over v minus v star, okay. And you say, well, what is the point in doing all this? Well, the point is that here you see why I said anisotropic diffusion. Now, the Fokker-Planck structure here is very clear. We have the divergence of some non-local, so local gradient, but no local diffusion in term, because the coefficient capital A is non-local, and it's anisotropic because inside capital A we have this matrix. So for some directions of gradient of f, it could be then the diffusion there is very small. And then we have the reaction term. The reaction term, which can be actually easier understood if we further rewrite this equation in non-divergence form, and if I apply the divergence into all the terms then I have inside, at the end we get something like this, plus f squared. So this is the formulation of the Landau equation, of the Landau diffusion operator, Landau operator, sorry, in divergence form, and this is the formulation in non-divergence form. So in any way, what we deduce from here, and something that perhaps was not clear at the beginning in the original formulation, right, with this huge integral, was that the Landau equation is actually a quasi-linear parabolic equation. Okay. With no local coefficients. With no local coefficients and a quadratic nonlinearity. Why should be f squared? Because so if I go from here, okay, so now when I apply the divergence, just look at the very end, okay, the very last term, we get the negative gradient f scalar product gradient little a, okay, but this term somehow cancels when I apply the divergence to the capital A. So that one, okay, doesn't matter, but then we have minus f Laplacian A. But if you remember what A was f of V star over V minus V star in dV star. So in 3 dimensions, this is actually the Ritz potential. So Laplacian A is actually negative f. And that's why we get the quadratic nonlinearity. Okay. And if we are in higher dimensions, the potential, so somehow this this here is modified so that at the end, no matter in what dimension you are, you always get an f squared. This is basically the way that the operator is built. Okay. Okay. No local coefficients. So the question that actually I will focus, the Landau equation has been studied since perhaps, I mean, was formulated, right, almost 100 years ago, and in many settings. What I will focus today and next week is actually, perhaps in my opinion, the most exciting question in this field. And it's the following dilemma: global well-posedness versus blow up in finite time. This is the main topic that I will be focusing on. And as of today, we don't know. So there is this very important open question. Okay. So with general initial data, this is very important. I will not touch upon situations in which initial data are close to equilibrium or are small in some norms. Those are somehow different questions, but with general initial data, so big in any norm, unbounded, whatever, with general initial data, do solutions stay regular for all time, or become unbounded in finite time? Okay. So this is something that is still open. Okay. And well, it's clear why we are saying blow up in finite time, right? Because of the term f squared, right? So that one can absolutely drive the f to become unbounded at a certain point. So if we look at similar equations, similar partial differential equations that have a similar, but let me say similar, maybe just in the writing, right? Not in the behavior. But so similar PDEs with to the Landau, at least in the formulation. So for example, the easiest one that we can think is the semi-linear heat equation. Well, and we know that the solutions to this equation, they blow up in any norm, including L1, okay? So then we can look, for example, at the semi-linear porous media. Okay. And the same for this PDE, we know that for certain range of M and P, we can have blow up and or global well posedness for the in the complement of those ranges. And the other one, for example, can be the Keller-Segal, which using the same notation and I used before, right, for Landau, the reaction term is exactly the same, right? It's exactly the quadratic nonlinearity, and then we have the Laplacian as a diffusion. So equation number 1, number 2, and number 3, okay, they all exhibit some type of singularity that happens at a certain point. Why the mathematical community strongly believes, right, that solutions stay regular, okay? But the first reason, and maybe the oldest, was that there is no numerical evidence, seems, right, Jose, correct me, but there is no numerical evidence that with some initial data, even very pathological, something really bad is going to happen. So this is something that seems is not happening, right? It seems that even with somehow not so smooth initial data, the equation regularizes itself. And the other reason is that unlike equation 1, 2, and 3, the Landau equation has this set of stationary solutions which are L infinity and 1, the Maxwellians. And this is not the case for 1, 2, and 3. So there is this too. And then another reason, perhaps, and this is a little bit more more recent, is that if we look at a similar equation, okay. So if you remember, so this is the Landau equation. So let me like this. Oh. Okay, so if I modified this equation a little bit, okay, and somehow I remove the anisotropy. So I do something like that. I take the trace of this matrix, capital A. So taking the trace means that you are basically removing the projection matrix here. Okay, and I'm basically removing this bad cone, the green cone, if you want to think this way. So by removing that, right, and so then we get something that A of f gradient f minus f gradient little a of f, or if you want to write it in non-divergence form, you get a non-local Laplacian plus f squared. So this equation here is globally well posed. Yeah.
So does it take phrase that you remove everything that's capital A of F is really small? So there's
Basically. Yeah.
Okay.
Yeah. I remove the degeneracy. The degeneracy happens only in a very small cone, right? It's actually, I don't care if I take the trace or the trace something very small in front, but I just removed that little cone. And then we get something that is still that still has a f squared term, right? But it's globally well posed. Now the question, yes.
But it doesn't have a Maxwellian equivalent.
No, by removing that projection matrix, I also remove this structure of the Maxwellian as a steady state. The steady state of this new problem is 0. Okay, I don't know, it is not clear if this is so relevant in terms of global well-posedness or not. The fact is that with this little trick, one can show that solution become stay regular. Okay, without it's not clear, and it's not understood if it's just a technicality or if somehow by removing that set something really pathological is taken out of the system, and then we get nicer solutions. Okay. So, but because of all this somehow hints and the things that that exist, then really I think the mathematical community is now more into trying to show that solutions stay bounded rather than try to show that there is blow up. So regarding this question, I would like to present 4 results that, in my opinion, as of today, they summarize pretty well what is the state of the art in this field. So there's so let me so state of the art regarding global well-posedness versus the blow up in finite time. Okay. For this one, I would like to actually introduce a more general Landau equation with less singular potential. Okay, so mimicking basically what is done for Boltzmann, in the literature, we have considered somehow more relaxed potential. So I'm going to use exactly the same structure, but now the A sub gamma of F, okay, is defined as this projection matrix over this V minus V star, but now I have a somehow a power here, okay, gamma minus 2 times F of V star dV star, and the little a gamma of F is the 1 over V minus V star to the minus gamma minus 2 F of V star dV star, and the gamma is a constant that is greater than -3 and less than 0. So -3 is the Coulomb potential, the one then we have just talked about until now. So you see the -3 is the worst case scenario, and then the potential becomes less and less singular. So what do we know about the issue of global well-posedness versus blow up in finite time for this model in this range of potentials here? Okay. Well, we know the following. So four results. Number one is that we have global well-posedness for gamma greater or equal than -2. Okay. So in that case, solutions are instantaneously smooth, a little bit like the heat equation. Think about like the heat equation. Solutions become instantaneously smooth and stay regular for all time. Okay. So the second result is a conditional global well-posedness for the more singular potentials. So conditional here means that the regularity is built upon an assumption on F, and this assumption is yet to be proven. And in particular, I can already, so one can do many assumptions, right? But what is, as of today, what is the somehow the easiest one? So the easiest one is, so in particular, we know that if our F is uniformly bounded in some LP norm, actually, when some high integrability in 3 dimension is 3/2. So if we know, if we know that our function is in L3/2 in the velocity variable uniformly in time, then we could immediately show that actually the solution, the function is L infinity in space and time. Okay. It's a 3 lines proof, this statement, and I will tell you later. But what is the condition? Well, the conditional is in this thing. We don't know if this is true. Okay. We only know as of today that our F is L1, nothing more. Okay. This is a big open problem. So after this result came out, actually, the problem is not showing then it's not L infinity, it's L infinity, but it's showing then you have somehow integrable with something slightly bigger than 3/2. So, but this result is conditional in one way, but you can read it also the other way. So in particular, it says that if you blow up in L infinity, you blow up in any norm until 3/2, right? So the blow up has to be quite extensive. Okay. So then the other 2 results, sorry, are, yes? If you are L infinity, then you become C infinity immediately. Yes, 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 absolutely. Yeah. The other result is on the for Coulomb, so for gamma equal to -3. So the this is not conditioned, this is a real one. So then the Hausdorff measure of the set of singular times is less or equal than 1/2. So weak solutions are regular except on a set of times with a measure less or equal than 1/2, which is a very similar results of the same of the Lere solutions for the Navier-Stokes system. And the similarity is also due to the fact that the Landau equation has a scaling thing that very much resembles the Navier-Stokes system. Okay, and then the last result, which is very much in line to the 4th one, is a very recent one, somehow about a year old, and is says the following: that there exists still for Coulomb. Okay. It's the sense of singular times. Yes, yes, yes. And there exists a T star, a time T star, that only depends on the mass, momentum, and entropy of the initial data. Okay, so initial data, okay, such that any weak solution after T star becomes regular. Okay. So this T star is somehow there is an estimate explicitly computable based on the mass, momentum, and the energy of the initial data. So the system, well, the beginning for any initial data, we have a short time existence of classical solutions. And then there is a certain time interval, the gray zone. We don't know what is happening there. But then at some point there is a T star after which solutions are regular again and will live forever. Okay. So if one looks for blow up, has to be in a certain time interval. Okay. And after that, it goes back to be regular and smooth, and they will be forever. So this result, so let me give you some references. So the number 4, the last result is by De Villette. Sorry. And then he and Zhang. In the preprint appeared in late 2020. I don't know if it's published already. So the number 3, so this result on the Hausdorff measure is by Francois Goltz, myself, Céline Berthe, and Alexis Vasseur, and it's been published, I think, recently. And the 1 and 2 somehow are very close related. And the first appeared by Louis Sylvestre in 17, and then with a completely different approaches by myself and Guyen in 19, and it's for both of them, for number 1 and in the same paper, as you see, exactly the same, different methods, but exactly the same results, and also the appearance, despite the different methods, the appearance of this minimal integrability regularity somehow. So I remember that last week, Jeremy, and he's not here, I don't know if in Zoom, was asking about, because Louis Sylvestre was talking about actually the result number 1, and then he was asking, do this, are they based on the, if they use entropy and estimate on the entropy production, right? And so the 1 and 2, no, because the 1 and 2 aim at showing global existence from the very beginning. So the methods used are really based on energy methods and standard regularity for parabolic and elliptic right away. But results number 3 and 4, they work with weak solutions. So they are really based on working with the only Lyapunov function, then you know that weak solutions satisfy, which is the entropy. So the result number 3 and number 4 are based on bounds on the entropy production. And number 4 actually presents a new somehow Lyapunov function, a new entropy, which is somehow the standard Boltzmann entropy plus a term which is involved the gradient at the denominator, so that could blow up and still be 0 anyway. So this is a new energy, and the estimates are based on the on bounding the entropy production. So very different, very different methods. Okay. How much time do I have? 10 minutes. Okay, so then I would like to give you a maybe a very single argument why for gamma greater than -2 we have global well-posedness. So the reason, there are many, there are several actually proofs in the literature. For example, by the proof by Luis Silvestre uses the version of the Landau in non-divergence form, and somehow a method by Krylov-Safanov of studying the contact set of some paraboloids that are above the solution with the real solution. And so the one that I would like to show you is based on the divergence form, and his somehow standard LP estimates. So, and the proof is really, really small. So let's see the global well-posedness for gamma greater or equal than -2. So, well, what I do, what we do, so we use energy methods. Okay. Energy methods, for example, let's do L2 estimates. So to do that, we take the equation, we multiply by f, integrate by parts, do integration by parts, and so on. And so then after a couple of lines, we arrive at something like this. So I have the derivative of the f square on the other side. Then we have the diffusion term, okay, the coercive term, the good term. And then we have the reaction term, okay, which I call now h of gamma. H of gamma is f, right, when we are at Coulomb, okay, because Coulomb we have a quadratic nonlinearity. If we multiply by f, we get f cube. But now when I remove when I am above Coulomb, then I don't have a square quadratic nonlinearity. I have f something times an average of f with some kernel, which is this h of f. So then the h is exactly, when gamma is greater than -3, is f of v star over v minus v star to the power negative gamma dv star. Okay. So the singularity becomes better and better if I increase the value of gamma. So now the question is, we have now the balance of two terms, the nice one and the polynomial one, which is not very good. So the question, if this is less or equal than 0, okay. If it is, we are done, basically, right? And so the question is that, do inequalities exist that guarantee this this sign? Well, actually, when gamma is greater than -2, okay, so if gamma is greater than -2, we showed, actually this was not known, but we showed that the following weighted Sobolev inequalities hold. And it's a family of inequalities. So that the integral, okay, of phi square weighted with h of f dv in R3 is less or equal, actually a small constant, times a diffusion term, a coercive term weighted by a of f, plus 1 over epsilon p square. Okay. For f, a function, I mean, for us, it's the solution of the Landau, but it doesn't matter. This is a general inequality, right? So phi is any function that makes the right-hand side bounded, L1, I mean, H1, compass support, whatever, smooth, whatever you want. And f is actually a function, then it's just L infinity in time, but L1 in space. Okay. And what is that epsilon? And that is the main thing. What is that epsilon? That epsilon is a constant as small as you wish. So somehow the nonlinearity can be bounded by a small term of the a small coercive term and somehow a penalty term. But the penalty term is of lower order, so it doesn't actually matter. We will have not control uniform in time of L2, but control of some e to the t times the L2 of the initial data. So that is no problem. And now you realize why, if we have this inequality, then if I substitute f for phi, right, then I get the control of my L2 or actually any LP. And once we have L2, we can go to L infinity, for example, by doing a truncation argument a la de George, and then from L infinity to C infinity using several things. Why this doesn't hold for, do I have one more minute? So this is just a remark, right? Because it's curious why it is, what happens when gamma is less than 2. The situation for gamma is less than 2, for example, for Coulomb, is not great, but it's not hopeless somehow in this regard. When gamma is, say for Coulomb, right, which is actually the important case, for Coulomb, what we can show, and this maybe shows the criticality of the Coulomb case, is that this is true. It's not and it's not true, but it's true for some constants C1 and C2. But those C1, this especially C1, is not small enough, then you can control the LP estimate. It's explicitly computable, right? It's a constant that depends on some ratio of quantities, but it's not small enough. So somehow the Coulomb case seems, if I can borrow the terminology from dispersive, seems a little bit critical, right? We have the effect of the diffusion is exactly the same order as the nonlinearity. And analytically, we don't know how to use that. It is clear that we have a diffusion, that the coefficient is big. When f is big, the diffusion is big, right? Because I have this capital A that becomes big when f is big, and so should control the nonlinearity. But how to translate this intuition then is not clear from the analysis point of view. So I think I should close here. Thank you very much.
From the on, you're watching the. Yeah, that's valid.
I should. Okay. So the most critical is -3, but critical in the sense of scaling. If you look, for example, at the so I can say that we have tried to look at this this modified this equation over here, right? So something like this, which in terms of scaling, it shouldn't matter. It's exactly the same thing. Okay. And for that one, actually, oh, let me close the chat. We could get a little bit lower than -2 using some type of Hardy inequality. No, I cannot get to -3. No. No, no, I could get to -3. Sorry, yes, I could get to -3 for radially symmetric. As this is the result, then I said, right? For radially symmetric, yes. For general, we could get below -2, but not really until -3. But There is just a matter of techniques that we are not able to do. Okay, it should be very easy, because if we can do it for radial symmetry, I mean, my intuition would be that is also true for general. It's not that the radial symmetry has to be bounded, or no, just even very bad ones. It's just that the radial symmetry helps in finding the mass function and working at the level of the mass function. The answer to your question is that it's not clear yet. If we should go on very close to -3 but not -3, or if -3 -2 is all a lump thing, you know, once you. No, yeah, exactly. So this is also what Luis said last week. Do not view the Landau equation as semi-linear, right? This is the end of the story, unless you are above -2. And -2 is basically the diffusion become constant. Your diffusion becomes like a Laplacian. But at that point, you don't have a quadratic nonlinearity anymore. So it becomes sort of like a heat equation with some linear term. Okay. When you have near Coulomb, no, the semi-linearity is out of the system, right? You should be viewed as you try to use the fact that you have a very big diffusion when your F is very big. But how to use that? Those type of weighted inequalities are very tricky because of this projection matrix. Yeah. Yeah. For radially symmetric so initial data. What we do is that we so we look at the mass function, and then we look at the equation for the mass function, and we do some barrier argument on the mass function. Yeah, it's not energy estimate. No.
Thank you very much for that.
The 3 halves.
Yeah.
This is related to gamma, right?
Oh yes, when you have gamma, you have something else. I mean, yeah, the 3 half was Coulomb. When you the closer you go to -2, the closer you go to 1.
Right. So in this way, it looks supercritical, right? Which is why all those other results that you wrote down.
You mean super? Yeah.
Look like